Okay, so I'm going to talk about the module about inquiry-based learning. So I did two sets, one of working about volume growth and one about continued fractions. And so inquiry-based learning is a little bit subtle. Well, I'm not saying that discovery-based learning or problem-based learnings are less subtle. They are as well very subtle. But the idea is here to have the students gather themselves in information and build some conjectures about what's happening. So it's easy to spoil an inquiry-based learning by saying too much. Okay, you never spoil it by saying too little, but then maybe nothing is going to happen. So it's a matter of balance between the two, right? So the first one about volumes. So it's a very early thing about volumes, right? So because students, they know the formulae and they can recite the formulae like a psalm or a song or something like that, but very often it doesn't make any sense. So this inquiry-based learning about volumes is in order to build a robust knowledge about volumes, especially the fact that a volume is linear in any of its dimensions. And since there are three, well, in everyday space, then if you make an enlargement, then it's going to impact the volume by its cube, all right? So, well, the first step 0 is introduction, having the students talk about volumes and about different types of physical quantities, length, area, volumes, and especially the way they double, right? So, and having them play with actually physical things, that is to say little squares and dice for the cubic volume, right? So this is a very short introduction for them to realize that when you double, okay, an area is not going to double, but to be quadrupled, okay, as we mathematicians know, but as the students usually, well, it's not so clear. So, and especially for the volume, when you double, the fact that you have 8 little cubes is not at all clear. And when you actually do it with dice, then you can count them and realize, okay, you say, you might think that this is finished, this is the end of it. But actually then when you go from simple cuboids to more complex shapes, you can see, I mean, if there are lower secondary math teachers among us or people who had the opportunity to test that with students, you can see that you have to do it all over again for other types of bodies. So the second step is to do this with other types of bodies. So for example, other cuboids that they actually built with paper, okay, or cones. Cone is my favorite. So, okay, so I don't know whether we have time actually to perform it among ourselves, but okay, so you construct, you choose an angle. Okay, so because this is the presentation, but it goes along with a worksheet. So let me present the worksheet. This is the structure of the module. Okay, so this is more intended for the teacher, and this is what should be discussed with the teachers. Okay, so this is all in the drive. So let me maybe first of all I put it in the chat so that you can find all the different files I'm talking about. This is the worksheet. And actually, so the worksheet on the volume, that's the part which should be given after appropriation by the teacher, which should be given to the student, okay? And so how to build a cone, a pyramid, or cylinder using paper and duct tape. So for example, for the cone, which is my favorite, you just construct, you just choose an angle, right? You choose an angle, and then you, with a compass, you choose a radius, and with a compass, you make a portion of a circular sector, okay, and you glue it back so that you have a cone of a given size, and you do it again, but with half of the size, okay. And you can do as well the same for a cuboid. Here I made the net of a cube, but you can make the net of something else, right? Choosing 3 different dimensions, and then you do the same, but for with half the size, right? And then you see how many times the smaller one goes into the larger one. You have to see for yourself that, for example, you use semolina, okay, and, or sand or whatever you can put in there, and you pour the little one in the larger one, and you count how many times you do that, and you end up seeing that it's 8, okay, and this 8 really is never showing up. I mean, in first intention, never. I mean, I've done that several times. Have you already done that, this kind of thing? So I mean, it's incredible because you do the thing with the dice, the number 8 comes out, okay, and then you change to the cone or to something, and you ask again the same question, and the 8 doesn't show up, okay, or maybe 1 out of 10, something of that sort. So it's pretty incredible. I find it, even after so many years, I find it always very disturbing. But okay, it's just that it's difficult to understand. All right. So you count, right? And if some are more are faster than others, then maybe you don't do an enlargement or a reduction by a factor half, but then you do an enlargement by a factor 3.5, okay, to see what happens, and you do it again, okay. But this is only for the one uh, um, who are faster, okay, because we all know that with these kind of students, you may have a great heterogeneity, and some may like it and be very fast, and some, okay, you have they will do it in their own time, okay. So that's for the second step. Okay, so the first step, step 0, is the introduction. Step 1 is this playtime thing with, and then the third step, step 2, is used on the sphere. So here you need balloons, inflatable balloons, and water. So it's a bit messy, but it's better to do it in Cyprus when it's hot outside. And you may work, I mean, I advise you to work with a digital camera, for example, with a smartphone, or maybe through a projection on the screen, where you can actually measure on the screen in order to be able to measure the size of your balloon, your inflated balloon. Okay, so holding it in your hand, pinching it with a hand and holding it with the other, it's approximately a sphere. And then you can measure its size, and then you empty it in a bucket in order to measure the height of the volume of water. Okay, and doing so, you end up having several sets of data with the volume of the balloon and the size of the sphere, and then you have to make a sense out of it. And we all know that making sense of such draw the graph of the volume growth, but they don't. They might not think about that. Okay, so well, it's then much more difficult to see the cubic growth, but okay. But it comes at the third step, and then the fourth step, which is step 3. Then, because I numbered at 0, like a French do with the ground floor and first floor, which is not the case here. In Cyprus, it's the English way. All right, so it's the volume of tetrahedron. Okay, that's origami activity, where you have a worksheet to help you fold paper and to construct with paper tetrahedra and octahedra. So maybe we can do the tetrahedron and octahedron together if you feel like it. So I am going to share this tetrahedron and octahedron worksheet. Okay, so please take a sheet of paper and fold it in two along the long side. All right, and then the second step is one there, and you have to till it reaches you have to first because you see the drawings of the crease is if it's plain, then it's a mountain, and if it's dotted, then it's a valley. All right, so here that means that it's the one on the middle is a mountain. So you have a mountain, and you have to fold this way. Okay, so your eyes have to be at two places at the same time. Okay, so you have to be sure that it's really in the corner, and you have to be sure that this corner meets at the middle. All right, okay. And with elder students, which is the case of the second part of the module, okay, then you can actually compute that because it's half, and because the cosine of a third of the flat angle is a half, then it is here, what we have here is a third of the flat angle. Okay, so you do that, and then you put it on the other side. This obtuse angle here, you're going to divide this obtuse angle into folding, that is to say, dividing this angle by 2. All right, and this is done on this side. Okay, you're going to fold this here, this to there. Okay, and we can actually witness that here we have a third of a flat angle, because you see that we have this flat angle here, which is divided in 3 parts. All right, okay, so everybody has that? It's okay? Sorry? Yes, okay, good. Okay, so we have this thing. All right, here we have to open it. Okay, and we have to do it in the other direction, but it's easier actually to do it in the other direction, because you see we have this point here, which we had to guess a little bit its position at first, but now we know exactly where to put the corner. We know exactly where to put the corner, because now we have, so the second side is way faster. All right, so of course doing it while walking among you is much easier than just doing it through Zoom. Okay, so you do it on the other side. Okay, and the thing is, you know where to put the corner, you know where to put it, because you already have it here, you see. So actually, okay, sorry about that. Okay, you can actually open it on your yes. Okay, all right, so now we have this, and so you're going to see that the other module is on the fact that an A4 is of ratio square root of 2. And here we're going to build a paper of size associated with square root of 3. Okay, it's not exactly square root of 3. We will see that it's associated with square root of 3, but it's not square root of 3. All right, and this part get rid of. Okay, we get rid of that part. And you have to do that twice. Okay, so now that you understand what we've done, you have to do it twice. Okay, so I have now this sheet of paper which folds naturally. You do it again. Okay, you take another piece of paper and you do it again. Sorry, so you do it again. Once again, you take one corner which is going to the middle strip, the middle. Okay, well, first you have to put it in. So have this. Maybe everything should have been creased and hills and not valleys here. Okay, I guess I did that wrong on the paper. Okay, and you get rid of the top thing. You done?
I hope so.
Okay. Sorry? Okay. Okay. Actually, so now we have enough to make an octahedron or a tetrahedron, but not both. Okay. So let's first do, because I think it's easier, an octahedron. So in order to make an octahedron, you have to make these little flaps here mountains, while all the others are valleys. Okay. So everything is valley except these two little things here, which are mountains. Okay. So in order to do that, you just take them and pinch them a little bit inwards. Okay. You pinch them a little bit inwards. Okay. And then this is going to take this shape. This shape. Okay. Okay. You see, it's going to take this shape. Okay. Here we are. Okay. To take this shape here. Okay. You don't get that? Because you have to well, I mean, whether you team together or because we have to make actually only one octahedron and many tetrahedra. Okay. So okay, so then you take these two. You have here one in one hand and the other one in the other hand, or else you are two. Okay, two people, and then you have to put these little things in these little holes. All right, so this here in this, and you have to alternate one inside and the other outside. Okay. Yes, maybe it's easier to do it together. Yes. So yes, you have two, and you make them just one face one another, so that you have four. You have, yes. Yeah, you have four like beaks, you know, you have beaks, but yes, you have these four beaks, and they have to, but open it up a little bit more. Yes. So, okay, and then all the beaks, they should go in another beak, but inside. Okay, and you should alternate inside, outside, inside, outside, for it to be strong. Okay, and this is going to make for you an octahedron. All right. Yes, I can see that Louise is almost there. Okay, so that's an octahedron. Okay, so we just need one octahedron. Okay, okay, so maybe we switch to the tetrahedron. Okay, have you succeeded? No, no. All right. Okay. So, okay, this is for the tetrahedron. It needs some practice, and now for the tetrahedron. For the tetrahedron, we're going to fold it yet another time. Okay, so that is to say, may I take yours? Yeah, yes, thank you. Because I mean, it's not a perfect octahedron, but I mean, at least it's there. All right. So now we're going to fold that along. So this is we fold that here and there. Okay, in order to have this shape. Okay. You see, one corner, two opposite corners, you fold them in, right, in order to have this. So you have to do it once left and the other right. Okay, that is to say, well, you have to do both rights, but you see, I take these two corners, okay, and for the other sheet of paper, I don't take these two opposite corners, I take these two opposite corners, okay? And you can see that it's not the same shape. It's almost the same shape. It's a symmetrical shape, but like my two hands are symmetrical, okay? It's the left and right chirality symmetry, okay? So you take two of these and you make one right and one left, and this crease here should not be a mountain, should be a valley. Okay, so this is going to make for you, when you fold everything, a little tetrahedron, but you need two, and this little beak is going into the other's little pocket here. Okay. Yeah. So okay, we did. So you can see that. No, let's do it. I want to show it. So here, for example, we did exactly the same. Okay, they are the same. It's not. They are not symmetrical. They are the same, which is not good. You have symmetrical. That's very good. Very nice. Yes, yes. Okay. What next? So let's fold them. Okay. All right. And then this crease here, you should make it a valley. Okay. Yes. Okay. Good. So you see that naturally it's going to fall this way if you follow the valleys. Okay. So you fold everything as valleys. Okay. So you have these two things, and here you have beaks here, and here you have pockets here. So you're going to put, well, actually, you begin with this pocket here. Okay. So you put this beak into that pocket, just till the end. You see, till the end. It's all the same shape, an equilateral triangle. Okay. Okay. And now you take that beak, okay, and you put it in that pocket. Okay. And then this one doesn't have a pocket, but it folds in. And this one, well, the rest folds in. Okay. And then you have a tetrahedron. Okay. Please do it. You get it? Okay, I can't. I'm not that happy.
I had one.
That's good. That's good. Good on you. Okay. So are they symmetrical? No. Here you should have followed the same form that we have. Oh, but this is not. This is still made for. Get it? Okay.
I
Stop. Okay. So no, that's all right. Don't make it personal. Let's do it again. It's okay. Mathematics is difficult. There is no denying that. And now, in order to make this octahedron thing, everything here is valid. Okay. These little segments here, I have to put them in the hill side. Okay. Yes, that's good. Yes, good. Okay, good. Okay, now that it's a mountain, then I can take them this way and up. Okay. Open it up a little bit. You see these beaks, they are going in these pockets. Beaks, pocket, beak, pocket. Yes. And then you have to carefully not messing things around. Let them properly adjust so that all equilateral triangles are going to fall into one another. Yes, please. You really have to do it like this with your fingers. Yeah. Just make your fingers like this. Good. But this one, okay. Did you miss something? No. This one. Folded in. But it's okay. Can you get the idea? All right? So that's for the octahedron. Let's do it apart. Okay. And then for the tetrahedron, you can take two opposite corners and put them in. Okay? But you Yes, and you see here they are exactly the same. Okay? Here, exactly the same, that's wrong. Okay? So one of them has to take the other. So we put that here, so now we put that here. All right? And this is a mountain. You should make it a valley. This one. Yeah? It's a mountain, make it a valley. No, contrary. Yes. You should do like this in order to. That's great.
This now it's French.
That's great.
This now it's French.
Okay. And now,
Yes. Okay.
now, okay.
And
So
now,
we are missing.
okay.
One.
So we're missing
Because
one.
the thing is, actually,
actually,
we cannot do exactly the same thing. So
So
out
out
of
of
four
four
tetrahedra and one octahedron, what do we do? I mean, just pretend there was one here, right? Okay. So yeah,
Missing one.
yes, we are missing one. So let's pretend we have one. What is this body here?
what is this?
What do we have?
What do we
It's not a triangle. There are many triangles. It's a pyramid, but it's not any kind of pyramid. I mean, pyramid of chaos, for example, has a square base. This has not a square base. So
This
it's a very typical pyramid.
So
Not
it's a
so
very
what
typical
what
pyramid.
is its name?
It's an Innomath.
What is
It's an Innomath pyramid.
Innomath.
Right.
Innomath pyramid,
It's an
okay.
Innomath pyramid.
Yeah, well, I mean, there are four faces.
Yeah, well, I mean,
In Greek,
there are
in
four
ancient
faces.
Greek, because now it's Tessera, no?
In ancient
Well, how do you
Greek,
call
because now
four?
it's Tessera, no?
Tessa.
Well, how do you call four?
Tessera. And
Tessera.
but it was
But it was
how was it in
Tetrahedron.
So tetrahedra. So it's a
Yes, so
tetrahedron.
tetrahedra.
Okay, 1,
So
2, 3,
it's
4. But it's twice as large. Yes.
But
Twice
it's
as large.
twice as large. Yes. Twice as
So
large.
what is the ratio of volume between
So
this
what's the ratio of
tetrahedron
volume
and this
tetrahedron
larger
and this
tetrahedron? I'm asking
large
you, if this was full gold,
If this
okay,
was
and
full
here
gold,
it's just paper, so it's not worth
here it's
nothing. But
just
let's
paper,
say
so
it's
not
full
worth
gold,
nothing.
right?
Let's say it's
And this is, let's say, one million euro. How many
1 million
would you
euro.
buy
How
this
many
thing?
would you buy this thing?
We don't have a lot. This one.
Huh, that's the issue.
This is a lot.
Uh-huh.
This is four.
That's the issue.
This is a three. I don't know.
Uh-huh.
But it's not only two.
So it's not only two. Clearly, it's not only two.
So it's not only two. Clearly, it's not only two.
So it's the same body as that one, right?
So it's the same body.
It is
as that
8.
one,
Yes.
right?
But this 8 is
It
not
is
natural.
Yes.
But this 8
It's not natural. Nobody finds
It is
this
not
8.
natural.
Nobody.
Nobody
Okay?
finds this
Even
eight.
even
Nobody.
even
Okay?
even mathematicians usually. I mean, if you
Even
stress them a little bit,
I mean,
give
if
them
you stress
off
them a
topic,
little bit, you
and
give
then
them
they
off
won't
topic,
find this 8. They will tell
and
you,
then
well,
they won't find this 8. They will tell you,
but it's 8. It's 8.
But it's 8.
Always
It's
8.
8.
If you take a body
Always
inflated by a
If you
factor
take a
of
body
2
inflated by a
in
factor
every
of 2,
dimension, then its
every
volume is going
dimension,
to be
then
8
its volume
times
is going to
larger.
be 8
And
times
this is
larger.
not at all,
And
not
this
at
is
all,
not at all, not at
clear
all, not at all clear.
for nobody.
For nobody.
And especially for the younger kids. So okay, it's 8.
It's 8.
And so this, where is this 8? We have 1, 2, 3, 4. Okay. And here we have 4. Okay. That means that the volume of this octahedron is exactly 4 times of this tetrahedron. And there is no way you can put that, I mean, you cannot. Okay? It's not the same shape, but you somehow demonstrated it. Okay? So that's the main topic of this module. But then there are other things to go with it. I don't know if if you heard me talking. Okay, fine. But okay, so that's the main topic, and it's accompanied by some. Okay, so it's accompanied with some GeoGebra thing. Okay, so derivation of growth. So we went through these things. So there is a GeoGebra book, the volume of the tetrahedron. Where is? I didn't put that here, the link. Okay, so I put the link. Okay, so there is a GeoGebra book. Okay, that I put the link in the chat. So which goes through that, but as a digital aid. Okay. So and which to some extent is going to show us. So I actually have a physical thing like this in Lyon, but as you saw, we can do it in origami, and then what it shows is this thing here, okay, where you actually derive a formula for the volume of a tetrahedron, okay. And how do you do that? Oops, sorry, it seems I'm not okay. Okay, actually there are several pieces, and there are 24 pieces, and these pieces, they are all tetrahedra. Okay, they are all tetrahedra, but only the golden ones that you can see now are regular tetrahedra. Okay, and all the others I don't well. Okay, this number tetrahedra, these other types of tetrahedra. Hello. There are actually these other types of tetrahedra. They are a quarter of an octahedron, and so they actually show that the volume. We're going to see that the volume of an octahedron is 4 times the volume of these golden tetrahedra, because, well, we just saw it with the double tetrahedron. Okay, so this is one. Okay, and then there are so what we just did together is this thing here, doubling the tetrahedron. Okay, so we have a tetrahedron with an octahedron, a regular octahedron. Okay, and so, well, okay, you can play with it and see for yourself, but actually I think it's better to do this origami procedure in order to see it, but that's just and now here is quarters of octahedra. Okay, these are quarters of octahedra, and you can look a little bit closer to these pieces, this quarter of octahedra, and how they look like. Okay, and they have 2 faces which are triangular equilateral triangles. Okay, and the 2 inner faces which are half squares. Okay, they are half squares. Okay, when you have the octahedron, actually it contains two squares, 3 squares in each dimension. Okay, and now we can see this. We can see now that these 2 pieces. This is the quarter of an octahedron. The quarter of an octahedron has 2 faces which are half squares and 2 faces which are 2 triangles. You can actually put it on the regular triangle base and play with the Cavalieri principle. The Cavalieri principle is making the summit move, but staying at the same height. Okay. So the Cavalieri principle show you that actually these 2 tetrahedra, while they have the different shape, they are actually of the same volume. Okay, so that ends the first module. Okay, you can go around that kind of things in different perspective. It depends on what the students are going to ask, which questions they are going to ask, and you can pull them in one direction or another. So this is just in written form. Okay, just what all I said is in written form with all the different things. But and so I polyhedra, okay, because these polyhedra you can do them as origami basis as we did, but as well as nets. That is to say, folding a piece of paper and having duct tape and putting them. So, and it's always as well a good thing to do that this way. Okay. And there are links in there. There are links to these GeoGebra animations. Okay, that was the first module, and actually the top of the module, that is to say the understanding this larger tetrahedron composed of smaller tetrahedra and octahedron is shared between the 2 modules. Okay, And so let's jump to the other module, share the presentation, and to switch. Okay, so we just did this. Okay, it's a simple volume growth of any shape, the volume of the tetrahedron, and arriving maybe not. Okay, it depends on the students. To this the volume of the tetrahedron with square root of a. If a is the side of the regular tetrahedron, square root of a to the cube divided by 24, because there are 24 tetrahedra to compose this large cube. Okay, they are all of the same volume. Hence, since the cube is, well, the size of the cube to the cube, the volume of each tetrahedron is 1/24 of this. Okay. That was and then it all ends up by a summary for modeling the growth of a volume, and the students have in their own word describe what they've learned. Okay, whether as text or maybe as some audio or as a graphic or maybe as a video or something of that sort. Okay? I mean, that's always a good way to end the module for the students to actually produce something telling what they just did. We should not miss institutional phase where you actually reflect on what you just did, because or else they say, okay, we just fold paper. That's all that will remain in their head. So we have to somehow make them conscious of the fact that they actually did some mathematics, and it was of some mathematic virtue. The second half of this inquiry-based learning is not for grade 7, but more for grade 9. And it's about continued fractions. Okay? So you may not be aware of continued fractions. Are you aware of continued fractions? Sorry? You will see. You will see. Okay, continued fraction. It's a way to encode numbers. Okay, with just integer numbers. So you can we are very used to encoding numbers through their decimal form. Okay, for example, pi is equal to 3,14159, etc. Okay, it is equal for us, but I mean there are many ways to actually encode it. Okay, so it's 3 plus a number which is less than 1. The rest being less than 1 means that its inverse is greater than 1. So it's 3 plus 1 over, well, a certain number which is greater than 1, which has an integer part, which is an integer number, plus a remainder which is less than 1. So it's 1 over. So it's 1 over plus 1 over plus 1 over. Okay, that's the continued fraction thing. All right. So, and we begin with an introduction about format, ratio. Okay, a number. What is a number? If I give you a stick is not associated to a number. Okay, it's associated with a number only if you know how to measure it with a unit. Okay, so a length is not a number, but a rectangle is a number. A rectangle actually encodes a number through the ratio of its width and length. Okay, so so it begins with having them reflect on 4/3. Does 4/3, the ratio 4/3, allow something in their head, or 16/9? Okay, 16/9 nowadays. Well, I mean, we know it's the ratio of this cinema type of projectors. Okay, this is a 4/3, I guess. But then it's we can see that, well, this screen here is a 4/3 clearly. Okay, but then we use it to beam a 16/9 on it. So we have to squish it a bit like that, you see. So, okay, a rectangle is associated with a ratio, and this ratio actually encodes a number. Okay, that's the introduction. And the second step is the A4 paper. Okay, my beloved A4 paper. It's beloved to me because I'm French. And you know why? No. Because actually, you know who invented this A4 paper and all these very nice properties? Do you know?
I
No, they are made for working in the magnification for photocopy machines.
Exactly, photocopy machines. And why did you need photocopy machines? Well, I mean, when the revolution in France came, well, there were some you had to put some big signs and smaller signs and things like that. And they said, okay, let's make something that doesn't change in size. Okay, and so the A4 paper is like the folded knife, right? And you fold it in two, you'll have another paper. But here it's in the A family, and the A family they are the same format. The A4 and A5 are on the same format, so I can actually do that with a camera, because I can, if I you can do that, is to say, to put the camera on the table and to put a ruler here and to say, okay, I'm putting that at 10 centimeters and I'm moving this and I'm going to do so that it's exactly at the same size, okay? And it's going to not overlap, not at the top, not at the bottom, not on the right. It's exactly again going to be exactly on top of it. Okay, it's not going to overlap in any, so it's the same shape, right? And you can actually see that. Okay, you can see that, but you can actually as well do it with a ruler. You just put them in the same corner. Okay, and you can see that. Okay, to have two points which are aligned, okay, is not so surprising usually. Okay, are you surprised when two points are aligned?
In that case, no.
Well, okay, 2 points are always aligned somehow, but here they are aligned because of the angles. Okay, so when these three are aligned, these three are aligned because it's a square angle. But now here, this diagonal, okay, these 3 points are aligned. Okay, which is not so clear. Okay, having 3 points aligned is something that should be noticed. I mean, okay, we have many. We live in a human environment, so the human made that lots of points are aligned, but I mean, in nature, somehow points are not aligned. And here, it's a piece of things made by man. So, okay, but it is a wonder that these 3 points are aligned, meaning that they actually are scale up from one another. And the A4 paper was done by the revolutionary, so that if you take two A4 paper, you have this A3 paper, which is of the same size. And then if you take two A3, you have an A2. And then for two A2s, you have an A1. And two A1, you have an A0, which is of 1 square meters area. Okay, that's the definition of the A0. The A0 is a paper of that particular ratio, and we're going to investigate what it is. So that its total area is 1 square meter. Okay. Yes.
Sorry, just you gave me an idea now. I don't know really how we can relate that. I mean, especially students to work with Plato. In one of the works of Plato, Meno, which is about, let's say, some social ideas about whether knowledge is an innate characteristic or not. Then they were asking a slave, if we double the side of a square, what is going to happen to the area of the square? Certainly, the first reaction of the slave was, it's going to be double, which is obvious.
Yes.
So really, these are very, very similar, and it's an opportunity really to see whether we can relate these ideas, which have to do with philosophical ideas, but also mathematical ideas as well. And at least for gifted children, is quite important.
I totally agree. I mean, Plato, Plateau is not at all clear, and it is very, very important. I totally agree. Doubling, I mean, okay, the scaling factor here is square root of 2, actually, and so this is the solution, but of course, I'm not going to do that. But it's the scaling factor, but it's as well the ratio. If you divide this by that, then you have an approximation of square root of 2. Okay? And but of course, it shouldn't be discovered somehow here. Okay. So the second step is to look at continued fractions. What continued fractions have to do with paper? So once again, with a worksheet which is somehow the solution. Okay. So you should not just bluntly give that to the students, or else it's going to not much benefits. Okay. But at any step, you should try to reach a conclusion somehow. Okay, so the conclusion of the introduction was that the ratio is a number and it can be pictured as a rectangle. So the A4, to notice that A3, A5, A4 have the same ratio. Okay, and so we're going to investigate this landscape A4. And so here comes the first step of continued fractions. So continued fractions, when you look at a number as a rectangle, well, this rectangle is whether elongated or a square or narrow. Okay, here you can see that it's elongated. That is to say, it's one square. My rectangle is one square plus something. Okay, so if some of you can do it, I just need two. Okay, so you see, it's one square plus an elongated strip. Okay, so I'm going to cut that at least to mark this this strip. Okay, so I have one square plus something. So my number is 1 plus something less than 1. Okay, this something less than 1 is actually, if I turn around this sheet of paper, okay, then the width becomes the length, and the length becomes the width. Okay, and as a number, that amounts to taking the inverse. Okay, 1 over. Okay, so now this narrow strip becomes a wide strip. Okay, so so please keep it. Yeah, just cut it. But I'm going to do the same here. That is to say, to try and see how many squares I can get out of this strip. Okay, I can get 1. Okay, but it's still elongated. I can get 2. Okay, so here so one has to be super tidy in order to do that right.
3, but you have always.
Yes, yes. I mean, always or not. Sometimes it stops. Yes?
But now not.
Now not.
I
Okay.
think you have to do it twice.
Aha, you have to do it twice, or
Or
maybe even
maybe
more
4
than
times.
that. Or maybe more than that.
8.
Maybe more than 8. Okay, so now you see I have 2 squares
It's always the same. Yes.
plus a little, it's always the same, but actually I have another strip, and can we compare these 2 strips? Thank you. These 2 strips, what do you think?
Yeah, they're similar.
They are similar. Okay, they are similar. Try to make it with a camera, so you can see that here
Yes.
almost, and we can, if you do it right, you can actually see geometrically that they are similar. Okay, or else you don't realize that they are similar, and you do it again, and you find there are 2 squares, and then yet another strip, and actually it's similar. Okay, but okay, and you can do it infinitely. Okay, and so what you get is actually so what you get here is, okay, so you put that in words, and so for the first thing you have that this ratio is between 1 plus half and 1 plus third. Okay, but if you do it one step more than that, then what you get is that it is actually this A here of the A for paper is not that nice. What has nicer continued fraction is 1 plus, and then 1 plus is it's each time you find, okay, you see, because here this strip here is 1 plus what we have. So if you add just 1 square, then you end up with this number. Okay, so this number is a really nice number because it was auto-similar. Each time you find 2 squares, you have a small strip which has the same. Okay, that means that is 1 plus 1. It's 2 plus 1 over 2 plus 1 over plus 2 plus 1 over 2 plus 1 over 2 plus 1 over. Each time it's the same. Okay, so that's the limit of it. Okay, all right. So can you figure out what number that is? So here, actually, what you have is, so can you give a meaning to this monster? This monster, because okay, we have no problems. We are used to giving a meaning like these 3 dots. Let's say a third is 0, 3, 3, 3, 3, 3 dots. And these 3 dots, okay, that means it's all the same. 3, 3, 3, 3. And we know that this has a limit. Okay, so here we have 2 plus 1 over 2 plus 1 over 2 plus 3 dots. There is kind of a monster here, you see. I mean, you should approach this with a little bit of caution, all right? So, but can we give a meaning to this? And yes, we can, because actually it's it tells you that this number fulfills this equation. 1 plus a is equal to 2 plus 1 over 1 plus a. Okay? Because at each time you can plug in. Where there is 1 plus a, you can plug in 2 plus 1 over 1 plus a. And you can do it infinitely. Okay? And so here, what I like to say is that doing mathematics is like taming dragons. Okay, taming dragons. You don't know whether a dragon exists. Okay, but if it exists, it has scales. Maybe it has a tail, or it has wings, or whatever. You take it, and then you pull it. Okay, and pulling it is you tell whatever you know on the dragon, and then this is called an equation. When you say enough on the dragon, then it's going to define it. When 1 plus a is equal to 2 plus 1 over 1 plus a, is that enough to define a? And yes, it is. Okay, you can reduce that over. You multiply everything by 1 plus a, and you end up with the fact that you have a squared is equal to 2. Okay, and a plus 1 squared and a squared is equal to. So a is actually, so that is to say the ratio of this a for paper is square root of 2. Okay, because you work out the fact that when you have this ratio and you square it, you have to, because it fulfills this. If you believe that it fulfills this equation, then you have that.
And the same is for A3 and B5.
Yes, they are of the same format, so it's the same square root of 2 thing. You can approach it from other angles, like for example, if you have P, which is the length of the paper, Q, which is the width, then what does it mean to fold it in 2? Okay, it means that whatever was what P is now replaced by Q, and Q is replaced by P over 2. Okay, and out of that you make an equation which gives you as well square root of 2. You can as well think about enlargements and area. Okay, if you have an area by a certain enlargement, then the area is the same area multiplied by the square of the number, and then this enlargement, because obviously we have exactly half of the material. Okay, we have exactly half of the material from A5 to A4. We have half of the material. Wow, double in the other direction. And so since we're considering the square of it, that means the enlargement is such that the square is 2. Okay, so it's square root of 2. Okay, I'm not going to dwell that much on that, but then you can do the same for other numbers. Okay, so here I take the square root, I give the GeoGebra construction here, where you actually characterize square root of n, okay, as being the ratio of a rectangle, so that if you divide it n times, no, this is not the one. This is just the continued fraction of the square root of n. Okay, so you have different continued fractions of square root of n. That was not the one I wanted to see. That was the other one. Let's go back to it. It was this one. Okay, and here this is to show that. Okay, so here I'm square root of 5. Okay, and actually there is, so whenever you have this continued fraction, it's infinite. Okay, it's infinite, or it is an integer. That is to say, it stops. Okay, and there is another way to look at it when you ask yourself, is square root of 5 rational or an irrational? Well, square root of 5 is defined by the fact that by the format of a rectangle, so that whenever you cut it in 5 vertically, then it is homothetic to itself. Okay, if it's homothetic to itself, then that means that it comes a certain integer number of times along the diagonal, and then there is an alternative, whether nothing remains. Okay, then that means that the square root is actually an integer. A square root of 9 is. Do you understand what is the square root of 9? What is it? Yes, that's good. Thank you. So, well, it's not that, I mean, I'm teasing, but okay. But okay, the thing is, a square root can be an integer. Okay, so square root of an integer of a perfect square, well, it's this square, it's the number. The square root of 9 is 3. Okay, so and that's what I'm going to see here. Root of 9. Oops, is 3. Okay, so you have 3 times this little rectangle, which fits in itself. Okay, and 9 is if you well, okay, you can see this rectangle as cut in 9 pieces, and each piece is exactly similar to it. Okay, so 9 is a perfect square. But if you take another number, then you see that is going to happen a certain integer number of times, but something remains. Okay, something remains, this little orange thing up there. Okay, but imagine that you had P and Q, the width, which were integers. Okay, just imagine that P and Q are integers in a certain unit. Well, P and Q of this rectangle, the green and the red are integer numbers. Okay, so of course, since let's go here, so you can see that this is 9 times. No, well, 10 times the green, so it's an integer, and this is 1 times the red, so it's an integer. Okay, so you have 2 integers. Okay, and now let's look at the end of it. Okay, so this orange thing must be an integer. The sides have to be an integer because the whole is an integer. Each little part, each red part is an integer. So the orange has integer sides, but they are smaller. You can see for yourself that they are smaller. Okay, and that's the way it's constructed. Hence, this cannot happen. That is to say, P and Q cannot be integers, because I mean, if you have a ratio which is an integer, you can always take the simplified quotient of the two. That is to say, to eliminate the common factors, and then you have the smallest numbers, integer numbers, with this ratio. Okay, and then this means that P and Q here cannot be integers. All right. So, okay. So maybe I'm a little bit fast here, but okay. That tells you that the square root of an integer is whether an integer number or an irrational. Okay, and then okay, since the Tetrahedra was talking about a piece of paper related to square root of 3, you can I finish this module by the same construction with origami. Okay, am I done with the time, or what is?
No, you have 25 minutes.
25 minutes here. Okay, so that means I can
It's cold here.
sorry.
It's cold here.
I
It's called
just
here.
I just made the fun lower.
Okay.
But
So this is explaining the worksheet, but as I said, I mean, giving it bluntly to the students might not be enough. Okay, and so might not do the trick. And so that's the worksheet, and to see the structure of let's summarize the structure of the learning plan, which is more structured than my presentation.
so could this example you gave us now with the A4, etc.,
Yes.
as an inquiry-based approach to start from the photocopy machine investigation, maybe for the
Yes.
students?
Yes, that could be a good starting point. Yes, because the thing is to not to tell them that the A5 is similar to the A4 is difficult.
They have to discover it.
Yes, so how to do that is I mean, they are so very used to it in Europe. Okay, I don't know whether in the States
In the States, they have a difference.
Yes.
They have the Likert size, it's called,
yes,
which is different dimension.
which doesn't have this property. So so I don't know exactly how to do that so that it's actually
So I guess their machines are different in the United States also, I think, probably.
probably they don't have these drawings that we have in Europe for the enlargement. This was the second part of it. So I divided that in different steps. Okay. And I guess it's really up to the teacher to actually see whether that fits his or her work strategy, because I think this is really very conversational. Okay, so okay, and as well, I think that closing with a reflection of the students on what they learned and this sort of things, for example, through a Padlet, or through voice messages, or through making a play out of it, I don't know. Okay, letting them express themselves, at least contribute to saying what they have to say. I thought that we would do this cone thing at the beginning, but actually I don't have the semolina. So
And the semolina is on this way, I think.
yes.
But,
So that's what I wanted to do. I mean, to actually see for yourself that there are 8 small ones in the large one, because it's so very not at all natural to my taste. So okay. So I think I will stop there, and maybe
okay, if there are any questions from the partners, from the participants, this is the time.
Christian would prefer to see demonstration with the balloon.
oh yes, with the balloon. Yes, yes, with the balloon. But I mean, you have to be to sit outside. I mean, near a sink, and here it's not the proper place to do that. To do it with a sink, and so you have to what the thing with the balloon, and you have to have this measuring jug as well. Okay, in order to know how much you've put in the balloon, but you have to have a ruler which you put alongside the balloon at the right depth, okay, with respect to the camera, okay, in order to be able to take a snapshot because if you put it before, then it's not going to be the right measure. So this
has to, you have to exert a little caution here. Okay, but apart from that, this works fine. Okay, and of course the thing is that these balloons, they are not self-similar, so their shape actually changes a little bit with their size. Okay, so this is you have to as well find the right range in which the balloon is almost self-similar. Okay, but it won't be. Okay, so that's another point as well, that mathematics can state perfect things on imperfect reality. Okay, reality, well, I mean, reality is reality. It has always right, but we put on reality some models. Okay, and these models are somehow perfect, but they're talking about a reality which is imperfect. Okay, so and relating to this perfection imperfection thing is really very important, I think. And I like this balloon thing, which is not a sphere, which is almost a sphere, but which can be modeled by a sphere. And it's a good idea to model it by a sphere or almost a sphere, right? So and some students, they may have lots of difficulties with that. They may think that mathematics is absolutely right, and there is no that it should be exactly the cube. Okay, the relationship from the size and the volume, it should be exactly the cube. It is not exactly the cube. It is somehow a good idea to model that by a cube. Okay, so yeah, that's another point to take into account.
Yes. What you showed us, Christian, is very interesting and very interactive. And I think we should try to implement in our classes these ways of teaching, because it's hands-on activity. Students can relate to what they're learning. And from my experience, I see the only problem with this is time. I don't know how it's in France or Germany or Poland or in Romania, but for us, time is an issue. We keep running to finish the material, to cover the syllabus, and we miss all these beautiful parts of mathematics, and we miss the chance to teach using different methods. But you gave us very nice ideas. Thank you.
Yes, okay. Thank you very much, Eleni. That's a very good point. You're right. The thing is, it can be done at some very special times, like at the end of the year, or some special times like that. And if you don't do that, then all the rest is useless. That's all there is to say. It's if you don't spend time giving meaning to mathematics, then mathematics are meaningless.
For me, I will do it in the first class of the year. No?
Yes, maybe on the first class of the year. You're absolutely right, Gregory. Yes.
Are there any other questions, or should we end this module at this point? Okay, thank you. Let me stop recording.